Hi everybody. Hi everybody. In this video we're going to learn how to analyze the graph of f using the graphs or equations of f prime and f double prime. Specifically, we'll develop tools to determine where f is increasing or decreasing, where f has a relative min or max, where f is concave up or concave down, and where f has points of inflection. For these first two, we will use something called the first derivative test. And the first derivative test, as you might be able to guess, uses f prime to determine whether f is increasing, decreasing, or whether f has a relative min or max. Alternatively, we can also use something called the second derivative test to determine, more specifically for relative mins or maxes, we can determine those using something called the second derivative test. As you might suspect, the second derivative test uses f double prime. That being said, however, the first derivative test is almost always going to be the preferred method, though you still have to be familiar with the second derivative test because there are times where the second derivative test applies. Then, for when we determine if f is concave up or concave down, or whether f has points of inflection, we are almost exclusively looking at the graph of f double prime, or the equations for f double prime, to do that. Furthermore, both the first and second derivative tests require us to know what critical points are. And so we will start our conversation today with what are critical points. Let's start our conversation with what it means for f to have a relative max or min. So if f has a relative maximum, that means that f is going from increasing to decreasing. So you can see here, alright, f is increasing here, f is decreasing here. At the top, that value is the maximum value. And it's relative because it's only happening in this little neighborhood. It is possible that the function might continue onward and get higher y values than the maximum value, but that's a different kind of maximum. It's not relative because even though these values are higher, this point here, for example, is not a relative maximum because there are higher y values beyond it. So relative maximum is where f changes from, and we can even say that here, f changes from increasing to decreasing. And this is nice because it appears on the fun chart. So if you redraw the fun chart over here, fun! It's so much fun to draw the fun chart every time. So good. Oh, this is f prime, this is f double prime here. Right here, f going from increasing to decreasing, that transition is a relative maximum. So we'll put that in red. And then the opposite, where f goes from decreasing to increasing, so let's do that here, f decreasing and then increasing, this is a relative min. The minimum would be in the bottom, right there. There are two ways that a relative maximum could happen. The first way is this nice, smooth function, and you notice I said smooth because this function here is differentiable, and we care about what the slope of the tangent line is at the top. Similarly, for a relative minimum, notice the slope of the tangent line at the bottom. So this is the first way that a relative min or max can occur, and that is for f prime of the x value, so let's call this x value c, and that is for f prime of c to be 0. Notice that these are horizontal tangent lines. And it makes sense because if you look at f prime for either a relative maximum or a relative minimum is changing from positive to negative or negative to positive. And what's the number between positive and negative? It's 0. So the first case where we will look for relative mins and maxes is by taking the derivative and setting the derivative equal to 0. Sometimes we won't actually find a relative min or a max because, for example, if you had x cubed, notice that here there is a horizontal tangent line, but this is neither a relative min nor a max, so we're going to figure out how that works later, but just know that just because the derivative is 0 doesn't mean that there is a relative min or max. The second way that a min or a max could occur is for there to be something like absolute value. So if you had a jaggedy graph like this, there are two values here. This is a relative max, and this is a relative min. Notice again that f goes from increasing to decreasing, and then here from decreasing to increasing, and therefore the graph of f prime goes from positive to negative and then back to positive in these regions of the graph. That being said, the derivative value at the top and bottom of this function are not 0 because they are sharp turns. The derivative at these c values is undefined. So, if we are looking for relative mins or maxes, we're going to look for whether the derivative is 0 or undefined, and these are going to be possibilities for those things. And these special yellow values are called critical points. So the definition for a critical point is f has a critical point. I can type. What now? At x equals c if f prime of c is 0 or if f prime of c is undefined. And I will also note that because it's a critical point at x equals c, this implies that there is a point c comma f of c on the function, and it also requires that c is in the domain of the function. So we might get values that seem like they're critical points, but they're actually not critical points because they're not points on the function. So you could a good example would be like y equals 1 over x. X here cannot be 0. 0 is not in the domain. If I take the derivative, negative 1 over x squared, notice that the derivative would be undefined when x is 0. This does not make 0 a critical point. However, we'll still have to take that into consideration when we do the first derivative test. Let's see this in action with an example. So let's say that we have the function f of x equals negative 2x cubed minus 6x squared minus 8. Let's go ahead and find the critical values. So we're going to take the derivative f prime of x, so negative 6x squared minus 12x minus 0, because the derivative of 8 is 0. And then because this function is defined for all x's, and we know that because the denominator of this function is 1, so the denominator can never be 0, that means that I'll set f prime equal to 0, so negative 6x squared minus 12x equals 0. And the best way here to solve this is to factor, so we're going to factor it. 0 equals negative 6x and then x plus 2. Notice that it's plus because I'm factoring the negative out here, and that means that this changes to a plus. And this gives me two critical points. It gives me c or x equals 0, and then here it gives us c equals negative 2. Here's what we're going to do with those values. We will construct a number line, and this number line is called a sign chart, sign with a G chart. And this is a sign chart for f prime because we're analyzing f prime. So we take our sign chart and we put our critical values on it in order. Notice that negative 2 comes before 0, so we put it there and there. For this first example, I would even suggest drawing vertical lines here between that so that we can have a sort of chart aspect going here. In the future, there will be better ways of doing this and you become more comfortable with it, but for these first few times, I want us to really understand what this chart is doing and what it means. Our goal is to determine whether or not f prime is positive or negative on each of the intervals here between these critical points. And the reason we want to determine if f is positive or negative is because if f is positive or negative, via the fun chart, we can tell if f is increasing or decreasing, and if we know that whether f changes from increasing to decreasing or decreasing to increasing, that's going to tell us if we have a relative min or a relative max. So the first thing we need to do is find test values. The only places where f prime could change sign are at the critical points. So I know that if I pick a point here, and a point here, and a point here, then the sign of f prime will be the same for that entire interval. So let's actually first decide what these intervals are. This first interval here is we'll even put that here, interval, is from negative infinity to negative 2. And notice that I'm using open parentheses, not closed brackets. Negative 2 to 0, and then from 0 to infinity. And then I have what's called a test value. So I'm going to pick a value in each of these intervals. So what's a number between negative infinity and negative 2? How about negative 3? And between negative 2 and 0, how about negative 1? And between 0 and infinity, how about positive 1? And notice I'm picking easy test values. What I'm going to do with my test values is plug them into f prime. So I'm going to do f prime of my test value, and that's going to tell me whether or not f prime is positive or negative on each of the intervals. So if I take negative 3 and I plug it into the first derivative here, I will get negative 6 times negative 3 times negative 3 plus 2. And really what I can do is, because I only care about the positive or negative aspect of this, I have a negative number times a negative number times a negative number. And 3 negatives equals a negative. So here at the top, I will make the conclusion that f prime is negative there. For negative 1, we'll do the same thing. We'll plug in negative 1 into f prime. So we will have negative 6 times negative 1 times negative 1 plus 2. So that's going to be a negative times a negative times, negative 1 plus 2 is a positive. Negative negative is a positive times positive. That means that f prime is positive here on this interval. And then in the last one, we have plugging in 1, negative 6, 1, and then 1 plus 2. Again, using the first derivative equation. This is going to be a negative number times 2 positive numbers, like that, which would be a net negative value. So this is important because it tells us what f prime is doing on each of these intervals. We're going to bring this down here to the bottom of the grid. So f prime went from negative to positive and back to negative. That means, using the fun chart, that f, not f prime, but the graph of f, graph of f went from decreasing to increasing and then back to decreasing. So we're going to make some statements about f using what we know about f prime. And this is how we want to construct these sentences for the AP exam and then, life in general. So here they are. The first statement is telling us, or is saying where f is increasing. So we can say that f is increasing on the interval negative 2 to 0 because f prime is positive on that interval. We did all that within this sign chart. We found f prime, we determined that f prime was positive. Here we have our interval negative 2 to 0, and that guarantees that f is increasing. So our because reason must reference the mathematics that we use to determine that. And because we use the equation for f prime, we're going to say that f prime is positive. Instead of saying on that interval, you could also just say there. This is also where you should not ever, ever, ever use the word it. So if you replace f prime with it, this is a no-no, because what is it? Is it f, f prime, f double prime, the graph, the equation, something? Though that's not a good phrase to put there. So words like it or the function or the derivative, because f prime is a derivative, but f double prime is also a derivative. So if you say f is increasing because the derivative is positive, that's not specific enough. The derivative of f has a name, and that name is f prime. So the best thing to put there is f prime because that's what you used. Okay, we can also say a sentence about how f is decreasing, so let's write that sentence. Our decreasing sentence would be f is decreasing on the two intervals negative infinity to negative 2 and 0 to infinity because f prime is negative there. I guess if I were writing this out, I would use the infinity symbol. Because I was typing, I used the word infinity, but that. You could also use union here for the and. You could also use inequality notation, so negative x less than, or negative infinity less than x less than negative 2, union 0 less than x less than infinity. That's fine. Also, here you could say because f prime is less than 0, but in the same vein as never use the word it, don't use f prime negative, as in the symbol negative, because that has a different mathematical meaning. So please, please, please use words. That's going to be the best way to communicate this. Okay, I recopied down our chart just so we could reference it. You don't have to redo this, just look back at your notes. So now we're going to justify where f has relative mins and relative maxes. So looking at f prime or f, the information here, we can tell that f has a relative minimum at negative 2, because if you notice, f goes from decreasing to increasing. And we're going to justify that using the following. We're going to say f prime has a relative or local, those mean the same, minimum at x equals 2 because f prime changes from negative to positive there. The sentence has several things that are important. First, we need to say where the minimum happens, that's at negative 2. And secondly, we need to justify it, and we're going to justify it using the fun chart language. We know that f has a relative minimum because f went from decreasing to increasing. How did we know that? We knew that because f prime changed from negative to positive, so we're going to write that out, f prime negative to positive in words, done. Does this graph have a relative maximum? Yes, it does. Right here at 0, f would have a relative maximum, so we're going to write that out. F has a relative or local maximum at x equals 0 because f prime changes from positive to negative there. These statements are using the first derivative test. What we're doing is we're using the information about the first derivative, f prime, changing from either positive to negative or negative to positive to justify whether or not f has relative minima or relative maxima. We can come to the same conclusion that we did using something called the second derivative test. And the second derivative test is a way to tell whether or not f has a relative maximum or relative minimum at a given critical point. The first thing we need to do that is to actually find the second derivative. So if I write f, we have f of x, which was negative 2x cubed minus 6x squared minus 8. Therefore, the first derivative was negative 6x squared minus 12x. Therefore, the second derivative of x is negative 12x minus 12. Okay, the process for this is almost the same. We first find the critical points, and if we do that, we are going to get x equals 0 and x equals negative 2 like before. But now, instead of constructing a chart, what we can do is find the second derivative and say, okay, we know that at x equals 0, one of three things could happen. Either it's a minimum and looks like this, or it's a maximum and looks like this, or it's neither and looks like this or this, like an x cubed function. So here and here, and in all four of these examples, the first derivative is 0, and that's like consistent with obtaining critical points. But the difference between these pictures is that in the first one, f is concave up at this specific value. In the second one, f is concave down, and in the second two, f is neither positive nor negative. And in fact, f switches from here from concave up to concave down, or here from concave down to concave up. That's a different thing that we'll talk about later. So in this first one, f prime of c was equal to 0, and f double prime of c is positive, and that is justification for a relative max. Nope, min, because it's at the bottom of the function. In this second case, f prime of c is also 0. Then we have f double prime of c is negative, and this is justification for a relative max. And then if f prime of c is 0 and the second derivative is also equal to 0, this is inconclusive. And if you get a function where the second derivative is 0, then you must go to the first derivative test or a different way to do that. The first derivative test is probably going to be the easiest thing to do, but it's inconclusive. It doesn't mean it's neither a relative min nor a relative max. It means you have to go do something else. So let's apply this to our example. We had x equals 0 was a critical point, and we're going to plug that into f double prime. And so if I take f double prime of 0, I can plug it in. Okay, negative 12 times 0 minus 12 is negative 12. So therefore we can conclude that because f double prime is negative, that's this situation here, which means that x equals 0, we have a relative max, which is exactly what we concluded over here. F has a relative max at 0. Our sentence for this would be a little bit different, though. It would look like this. F has a relative max at x equals 0 because f prime of 0 is 0. That satisfies the critical point aspect, and then the second derivative test is that f double prime of 0 is negative, making f concave down, making 0 be a maximum because it's at the top. Let's do the same for x equals negative 2. So if I take negative 2, we're going to plug that into f double prime of negative 2, and that's going to be equal to negative 12 times negative 2 minus 12. Negative 12 times negative 2 is 24, positive. And then minus 12 is positive 12, so we have the opposite result here. So because f double prime is a positive value, that is this situation here, where f prime is 0, f double prime is positive, therefore negative 2 is a relative minimum, so we write out a sentence and it looks very much like the first one, except with different words. F has a relative minimum at x equals -2 because f prime of -2 is 0 and f double prime of -2 is positive. Notice that we are using -2 as the x value, just like we use 0 for the x value here. Alright, let's talk about the second part of this, which is f having points of inflection, or where f is concave up or concave down. And if we look back at the fun chart, we can see that for this, we're going to be using f double prime for the most part, especially when we have equations. So because when f double prime is positive, f is concave up, and when f double prime is negative, f is concave down, that's going to be our best way to justify this. So essentially we're going to do the same thing, except instead of constructing a sine chart with f prime, we're going to construct a sine chart with f double prime. Well, we already have f double prime. It is negative 12x minus 12. And so we set the second derivative equal to 0 because we want to see where f double prime could change sign, and that's going to be where f double prime equals 0 or f double prime is undefined. Now, there's no word for this, like these are not critical points. Critical points are only for f prime. I like to call these possible points of inflection, but there's no mathematically defined term for what these points are when f double prime is 0 or f double prime is undefined. Possible points of inflection. So this is like a DRAM only thing, and yeah, whatever. So we take f double prime, we set it equals 0, and again, by factoring, we can see that if we factor out a -12, we get x plus 1, and then solving this, we get x equals -1. So our chart is actually very straightforward. So sine chart, here's -1. We have two intervals. The first interval is -infinity to -1. The second interval is -1 to +infinity. And in the same way, we have intervals. We are going to pick a test value. So for -infinity to -1, we'll pick -2. And from -1, sorry, that's a 1 out of 4, we'll pick 0. That's not too bad. And then we'll do f double prime of our test value. So if I do that, I'm going to have -12 times -2 minus 12. That's going to be, oh, we already did this calculation. It's 24 minus 12, which is a positive value. And here with 0, it's -12 times 0 minus 12, which is a negative value. That means that f double prime on these intervals are positive and then negative respectively, which means that f is concave up and concave down on these intervals like that. So our sentences are actually pretty straightforward. We can write them right away. We can say that f is concave up on -infinity to -1 because f double prime is positive on that interval. F is concave down on -1 to infinity because f double prime is negative on that interval. And you notice the structure. We have f, we have the property, we have the interval, then we have because, and that's important, and then we have the function we use, either f or f double prime, and then the property of f prime or f double prime that we use to justify. The last thing we're going to talk about here is the points of inflection. Inflection points happen when f changes from concave up or concave down or vice versa. So changing from concave up to concave down or vice versa, which means that on f double prime, positive to negative or vice versa. So our sentence here will be very similar. F has a point of inflection at x equals -1 because f double prime changes from negative to positive or vice versa there. Here, again, we have function, property, interval or location, because, and then what did we use? We used f double prime, and then the property here is that f double prime changes from negative to positive or vice versa. And this is only where this vice versa relationship is true. F concave up, concave down, f double prime plus minus, or f prime increasing, decreasing. A point of inflection happens when any of these three things happens, and it doesn't matter the order in which they happen. So if f double prime went from negative to positive, that is also a point of inflection because f double prime would be concave down changing to concave up, sad, happy. Right here in the middle would be the point of inflection on the graph of f. So we can throw in that vice versa only for points of inflection, but still making sure to use the correct, f prime positive to negative. We're using f prime positive to negative, and we're choosing to use positive to negative because we have equations and it's easy to set up a sign chart for that. Hope you enjoyed this video. Come with questions, and yeah, we'll take care of things. Have fun!